Hello everyone, welcome back to my channel. I am Jyotsna, pursuing my BE Computer Science from Sri Venkateshwara College of Engineering. Today's topic is applications of differential equations. Topics to be covered are introduction, applications of differential equations, types of differential equations, linear equations, Bernoulli equations and exact equations. Differential equations. A differential equation is an equation that contains at least one derivative of an unknown function, either an ordinary derivative or a partial derivative. Suppose the rate of change of a function y with respect to x is inversely proportional to y, we express it as dy by dx is equals to k by y. In calculus, a differential equation is an equation that involves the derivatives of dependent variable with respect to independent variable or variables. The derivative represents nothing but a rate of change, and the differential equation helps us present a relationship between the changing quantity with respect to the change in another quantity. Y is equals to f of x be a function where y is a dependent variable, f is an unknown function and x is an independent variable. And this is how a differential equation looks like, and here are some other few examples of differential equations. Applications of differential equations. Ordinary differential equations applications in real life are used to calculate the movement or flow of electricity, motion of an object to and fro like a pendulum, to explain thermodynamics concepts. Also in medical terms, they are used to check the growth of diseases in graphical representation. Differential equations are useful in describing mathematical models involving population growth or radioactive decay. In describing the equation of motion of waves or a pendulum, there are various other applications of differential equations in the fields of engineering, physics, chemistry, geology, economics, and etc. Types of differential equations: linear equations, Bernoulli equations, exact equations. First one, linear differential equations. Q are numeric constants or functions in x. It consists of a y and a derivative of y. The differential is a first order differentiation and is called the first order linear differential equation. This linear differential equation is in y. Similarly, we can write the linear differential equation in x also. The linear differential equation in x is dx by dy plus p1x is equals to q1, and the linear differential equation in y is dy by dx plus py is equals to q. Here are some other examples of linear differential equations in y and linear differential equations in x. Steps to solve linear differential equations. The following three simple steps are helpful to write the general solutions of linear differential equations. Step 1. Simplify and write the given differential equation in the form dy by dx plus py is equals to q, where q and p are numeric constants or functions in x. Step 2. Find the integrating factor of linear differential equation if is equals to e to the power integration of p dot dx. Step 3. Now we can write the solution of linear differential equation as follows. Y multiplied with integrating factor is equals to integration of q multiplied with integrating factor dot dx plus c. Second one, Bernoulli differential equations. In this section, we are going to take a look at differential equations in the form y plus q of x y to the power n, where p of x and q of x are continuous functions on the interval we are working on and n is a real number. Differential equations in this form are called Bernoulli equations. First, notice that if n is equals to 0 or n equals to 1, then the equation is linear, and we already know how to solve these cases. Therefore, in this section we are going to be looking at solutions for values of n other than these two. In order to solve these, we will first divide the differential equation by y to the power n to get this equation, which is y to the power minus n y dash plus p of x multiplied with y to the power 1 minus n is equals to q of x. We are now going to use the substitution v is equals to y to the power 1 minus n to convert this into a differential equation in terms of v. As we will see, this will lead to a differential equation that we can solve. We are going to have to be careful with this, however, when it comes to dealing with the derivative y dash. We need to determine just what y dash is in terms of our substitution. This is easier to do than it might at first look to be. All that we need to do is differentiate both sides of our substitution with respect to x. Remember that both v and y are functions of x, and so we will need to use the chain rule on the right side. If you remember your calculus, you will recall this is just implicit differentiation. So taking the derivative gives us v dash is equals to 1 minus n multiplied with y to the power minus n y dash. Now plugging this as well as our substitution into the differential equation gives 1 by 1 minus n v dash plus p of x v is equals to q of x. This is a linear differential equation that we can solve for v, and once we have this in hand, we can also get the solution to the original differential equation by plugging v back into our substitution and solving for y. Third one is exact differential equations. The equation p of x comma y dx plus q of x comma y dy is equal to 0 is an exact differential equation if there exists a function f of two variables x comma y having continuous partial derivatives such that the exact differential equation definition is separated as follows. Ux of x comma y is equals to p of x comma y and uy x comma y is equals to q of x comma y. Therefore, the general solution of equation is u of x comma y is equals to c, where c is an arbitrary constant. Steps to solve exact differential equations. The following steps explain how to solve the exact differential equations in detailed way. Step 1. The first step to solve exact differential equation is to make sure with the given differential equation is exact using testing of exactness. dq by dx is equals to dp by dy. Step 2. Write the system of two differential equations that defines the function u of x comma y, that is du by dx is equals to p of x comma y and du by dy is equals to q of x comma y. Step 3. Integrating the first equation over the variable x, we get u of x comma y is equals to integration of p of x comma y dx is plus psi of y. Instead of an arbitrary constant c, we write an unknown function of y. Step 4. Differentiating with respect to y, substitute the function u of x comma y in the second equation. Du by dy is equals to d of dy integration of p of x comma y dx plus psi of y is equals to q of x comma y. From the above expression, we get the derivative of the unknown function psi of y, and it is given by psi of y is equals to q of x comma y minus d by dy multiplied with integration of p of x comma y dx. Step 5. We can find the function psi of y by integrating the last expression, so that the function u of x comma y becomes u of x comma y is equals to integration of p of x comma y dx plus psi of y. Step 6. Finally, the general solution of exact differential equations is given by u of x comma y is equals to c. Finally, thank you for watching this video. Please like it and share it with your friends and family.